Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Welcome to another episode of Ben Keefe the Science Geek with yours truly, Ben Keefe the Science Geek. Today we're going to be talking about SN2 reactions. SN2 stands for substitution, nucleophilic, and bimolecular. Now, this means that it's a nucleophilic substitution and the reaction is bimolecular, which means that the rate determining step has two molecules. Here's an example of a basic SN2 reaction. In this case, the nucleophile OH- from the SN2 will attack the central carbon in this molecule here and kick out the leaving group, bromine. Bromine is a good leaving group because it has a relatively weak bond with carbon and is fairly electronegative, so it holds its electrons well. This reaction creates this molecule you see over here, an alcohol, and a bromine ion as a byproduct. The energy diagram depicted here shows that the reaction happens in one step or is concerted. The top point of the energy diagram is the transition state, which is shown on the right here. In the transition state, you can see that the OH, or the nucleophile, is pushing the bromine leaving group out from the back. This is called a backside attack and has some interesting implications with stereochemistry. And here today to talk to us about the very interesting implications of the stereochemistry of SN2 reactions, we have resident expert Jacob MacNeil. Welcome, Jacob.
Thanks for having me on the show.
Thank you very much for being here.
SN2 reactions, they're inverted.
Inverted? What does that mean?
In all seriousness, being able to predict the stereochemical outcome of an SN2 reaction is an important skill. In the reaction which we just saw, listed above here, the OH nucleophile attacks the back of the carbon and forces the Br leaving group out. This causes the surrounding groups to be flipped. In this reaction, it doesn't have an effect, but in a reaction where the central carbon is a chiral center, this has an effect on stereochemistry, and it is an inversion. Shown here, the central carbon is a chiral center with 4 different groups surrounding it, and it's the S enantiomer. When we add the OH and the SN2 reaction and it attacks the back of the carbon, the resulting 3 groups are flipped when the OH adds and the Br is forced out. This causes the enantiomer to be an R enantiomer, and it's an inversion from the original S enantiomer. This means that the SN2 reaction is what's known as a stereospecific reaction. This means that for a given enantiomer, the opposite enantiomer is received as a product. This has very important applications and can be used to make a desired enantiomer in organic synthesis.
What if you have something like this, though? How does it get through all these big groups?
That's a great observation. It actually doesn't.
But why?
This alkyl bromide has a 3' carbon, and therefore it will not go SN2 because the nucleophile, which is adding from the back side, is sterically hindered and can't make it to the central carbon. SN2 reactions prefer to have a primary carbon, not a big bulky 3' carbon, because it's much easier for the nucleophile to add. One easy way to tell if it's an SN2 reaction, as well as the stereochemistry, is the kinetics of the reaction. Because the reaction is bimolecular, meaning there are 2 molecules in the rate determining step, adding double either the alkyl bromide or the nucleophile will double the rate of the reaction. If the rate of the reaction doesn't double when either the alkyl bromide or nucleophile are doubled, then we could be looking at a different type of reaction.
What other types of reactions is there?
Next time on Ben Keefe the Science Geek, we'll talk about other types of reactions like SN1, a unimolecular reaction where the rate, in this case, would only depend on the alkyl bromide. Thanks for watching.
Bill Nye the Science Guy. Bill Nye